Look up at the night sky on a clear evening, far from the light pollution of cities. What do you see? A tapestry of stars, seemingly fixed, unchanging. Yet, this serene tableau hides a profound truth. The universe is not static. It is a canvas in constant motion, an entity experiencing an epic, accelerating journey that began billions of years ago and continues to unfold towards an unimaginable future. Our current moment, with its vibrant galaxies and life-giving stars, is but a fleeting chapter in this cosmic saga, a precious interval before the universe potentially descends into an eternal cold void. To comprehend its ultimate fate, we must first understand its current, dynamic state, a state defined by relentless expansion. For centuries, even millennia, humanity largely conceived of a static, unchanging cosmos. Our observations, limited to the naked eye and early telescopes, revealed stars that seemed to hold their positions relative to one another, forming constellations that persisted through generations. The grand nebulae, those ethereal smudges of light, were thought to be gas clouds within our own galaxy, the Milky Way. This view of a stable, perhaps even eternal universe began to crumble in the early 20th century, challenged by groundbreaking astronomical observations that would fundamentally reshape our understanding of reality. The first hints of a non-static universe came from Vesto Slipher, an American astronomer who, starting in 1912, meticulously measured the spectra of light from these spiral nebulae. He observed that the light from most of them was shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift, he correctly interpreted, was a manifestation of the Doppler effect, indicating that these nebulae were moving away from Earth at tremendous speeds, some exceeding 1,000 kilometers per second. It was a revolutionary finding, suggesting a universe in motion, but its true significance wouldn't be fully grasped until another astronomer connected these motions to cosmic distances. That astronomer was Edwin Hubble. Working from the Mount Wilson Observatory in California, equipped with the then largest telescope in the world, the 100-inch Hooker telescope, Hubble embarked on a monumental task, measuring the distances to these enigmatic nebulae. His breakthrough came in 1923, when he identified Cepheid variable stars in the Andromeda Nebula. Cepheids are a special type of star whose luminosity, or intrinsic brightness, varies with a regular period. Crucially, Henrietta Leavitt had earlier discovered a direct relationship between a Cepheid's period of pulsation and its absolute luminosity. By observing a Cepheid's pulsation period, astronomers could determine its true brightness, and by comparing this to its apparent brightness as seen from Earth, they could calculate its distance. Hubble's measurements unequivocally showed that Andromeda, and subsequently many other spiral nebulae, were not gas clouds within our own galaxy, but separate island universes, entire galaxies, billions of light-years away. With distances firmly established, Hubble combined his findings with Slipher's redshift data. In 1929, he published his seminal work, demonstrating a direct correlation. The further away a galaxy was, the faster it appeared to be receding from us. This relationship, now known as Hubble's law, or more accurately, the Hubble-Lemaitre law, acknowledging Georges Lemaitre's earlier theoretical work, provided the first compelling observational evidence for an expanding universe. It was not merely galaxies flying through empty space, but space itself expanding, carrying the galaxies along for the ride, much like raisins embedded in a rising loaf of bread. Every raisin moves away from every other raisin as the dough expands, without any individual raisin actually moving through the dough. This cosmic expansion implies a beginning, a moment when all matter and energy in the universe were compressed into an incredibly dense state, an event we now call the Big Bang, which occurred approximately 13.8 billion years ago. For decades, the standard cosmological model predicted that the expansion of the universe, driven by the initial impetus of the Big Bang, should be gradually slowing down due to the gravitational pull of all the matter within it. Imagine throwing a ball into the air. It slows down as gravity pulls it back towards the Earth. Similarly, the mutual gravitational attraction between galaxies was expected to act as a cosmic brake, decelerating the expansion. Scientists even debated whether the expansion would eventually halt and reverse into a big crunch, or simply continue to slow down indefinitely. This prevailing understanding was overturned by a series of astonishing discoveries in the late 1990s, fundamentally altering our perception of the universe's ultimate destiny. In 1998 and 1999, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were independently studying distant type Ia supernova. These particular supernova are invaluable standard candles for cosmologists. They originate from white dwarf stars in binary systems that accumulate matter from a companion star. When a white dwarf reaches a critical mass, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, it undergoes a runaway thermonuclear explosion, briefly outshining entire galaxies. Critically, because they all explode at roughly the same mass and through the same mechanism, type Ia supernovae are believed to have a remarkably consistent intrinsic peak luminosity. This means that by measuring how bright they appear from Earth, astronomers can determine their distance with high precision. Both teams were using these cosmic beacons to measure the expansion rate of the universe at different points in cosmic history. They expected to find evidence of a decelerating expansion, consistent with gravity's influence. Instead, their data presented a perplexing and revolutionary result. The distant supernovae appeared fainter than they should have been if the universe's expansion was slowing down. Fainter objects are typically further away. This implied that the galaxies hosting these supernovae were further away than predicted by a decelerating universe, meaning the universe's expansion was not slowing down, but rather speeding up. The expansion was accelerating. This discovery sent shockwaves through the scientific community. It meant that some unknown force was actively pushing galaxies apart, counteracting gravity's pull, and causing the universe to expand at an ever-increasing rate. This mysterious entity was given the name dark energy. It is not to be confused with dark matter, which is a gravitational clumping form of matter that interacts only weakly with normal matter and light. Dark energy, by contrast, acts as a repulsive force, an inherent property of space itself, exerting a negative pressure that drives the accelerated expansion. Imagine blowing into a balloon, but instead of the air pressure decreasing as the balloon expands, it somehow stays constant, continuing to inflate the balloon at an ever faster rate. That's a simplified way to think about how dark energy might work. Current cosmological models estimate that dark energy constitutes approximately 68% of the total energy density of the universe. For comparison, dark matter makes up about 27%, and ordinary matter, the stuff that makes up stars, planets, and ourselves, accounts for a mere 5%. This means that the fate of the universe is overwhelmingly dictated by this enigmatic, pervasive force. Dark energy is not clumping into structures. It is spread uniformly throughout space, and its density appears to remain constant even as space expands. As the universe grows larger, the amount of dark energy within it effectively increases, because there's simply more space for it to occupy, leading to an ever stronger repulsive effect. Understanding the nature and behavior of dark energy is therefore paramount to predicting the universe's long-term evolution. If dark energy's influence continues to dominate, it will drive the universe towards a future vastly different from the one envisioned before its discovery. The delicate balance we observe today, gravity successfully forming stars and galaxies, yet dark energy pushing them apart on the grandest scales, is a temporary one. This vibrant, structured universe we inhabit, teeming with light and activity, is a snapshot in time. It is an evolving system, and the acceleration of its expansion is the engine driving it towards its ultimate, cold, and empty destiny. By grasping the mechanisms of cosmic expansion and the role of dark energy, we begin to lay the groundwork for understanding the profound changes that await the cosmos billions and trillions of years from now. Having established the universe's accelerating expansion, driven by the mysterious force of dark energy, we now turn our attention to the fundamental principle that dictates the ultimate fate of all matter, energy, and structure within this ever-expanding cosmos. This principle is entropy, and its relentless increase guides the universe towards an inevitable, chilling conclusion, known as heat death. Imagine a meticulously organized room. Every book is on its shelf, every item in its place. Now, imagine a year passes without anyone tidying it. The books have fallen, clothes are strewn, dust gathers. The room has moved from a state of order to disorder. This everyday experience provides a simple analogy for entropy, which, at its core, is a measure of disorder or randomness within a system. More precisely, in the realm of physics, entropy quantifies the number of different microscopic arrangements that correspond to a particular macroscopic state. If a system can exist in many more ways at a microscopic level, while still appearing the same to us macroscopically, it has higher entropy. A single ice cube, for instance, has relatively low entropy because its water molecules are locked into a rigid, ordered crystal lattice. Melt that ice cube into a glass of water, and the molecules are now free to move and arrange themselves in a vastly greater number of configurations, corresponding to a much higher entropy. The water molecules haven't disappeared, but their energy and arrangement have become more dispersed and less ordered. This natural tendency towards increased disorder is not just an observation. It is enshrined as one of the most fundamental laws of nature, the second law of thermodynamics. This law states that the total entropy of an isolated system can only increase over time, or at best remain constant, but it can never decrease. The universe, in its entirety, is considered the ultimate isolated system. There is nothing outside of it to influence its overall energy balance or organizational state. Therefore, the second law applies to the cosmos as a whole, dictating an inexorable march toward greater disorder. This fundamental principle is what gives time its direction, often referred to as the arrow of time. We remember the past, but not the future, because the past is a state of lower entropy from which the universe has progressed. A dropped glass shatters, increasing the system's entropy. It never spontaneously reassembles. Sugar dissolves in coffee, but it never spontaneously reforms into a cube. These are all manifestations of the second law at work. What does this mean for the universe? All processes that occur in the cosmos, from the nuclear fusion in a star's core to the chemical reactions that power life depend on energy gradients. They require a difference in temperature, pressure, or chemical potential to function. A star shines because its core is immensely hot and dense, allowing energy to flow outwards into the cooler vacuum of space. A planetary atmosphere circulates due to temperature differences between the equator and the poles. Life itself is an intricate, highly ordered system that locally reduces entropy by consuming and transforming high-grade energy, like sunlight, and releasing low-grade energy, heat, back into its environment, thereby increasing the overall entropy of the larger system. All work, all motion, all change relies on these gradients. The second law of thermodynamics tells us that these gradients are constantly being smoothed out, energy is being dispersed, and the universe is slowly but surely heading towards a state where all such differences have vanished. This ultimate state of maximum entropy, where all energy is evenly distributed and no work can be done, is known as heat death. It is a chilling concept, envisioning a universe where everything has reached thermal equilibrium. Picture a vast ocean where the temperature is precisely the same everywhere, from the surface to the deepest trench. No currents would flow, no waves would break, no differences would exist to drive any motion or change. In the cosmic context, heat death means a universe where there are no hotspots like stars, no cold spots like the deep vacuum of space, no dense regions like galaxies, and no dilute regions. All matter and radiation would be spread so thinly and uniformly that the entire cosmos would exist at a single, incredibly low temperature, approaching absolute zero, which is 0 Kelvin, or approximately 273.15 degrees Celsius. In such a state, there would be no energy available to power any process, create any structure, or sustain any form of life. The universe would not be dead in the sense of having ceased to exist, but rather dead in the sense of being utterly inert, devoid of any potential for activity or evolution. The role of dark energy, the mysterious force behind the accelerating expansion of the universe, becomes critically important in this scenario. While entropy is an intrinsic property of any system, dark energy acts as a catalyst, ensuring and accelerating the universe's descent into heat death. By relentlessly pushing space apart, dark energy actively dilutes matter and radiation across an ever-increasing volume. As the universe expands at an accelerating rate, the average density of particles and energy decreases. This means that any existing energy gradients already destined to dissipate due to the second law are stretched thin and weakened even faster. Galaxies, once vibrant clusters of billions of stars, will eventually become so far apart that they can no longer interact or even see each other. The light from distant galaxies will be redshifted into oblivion, their energy spread across an unimaginable expanse of empty space. Consider the energy of a photon, a particle of light. As the universe expands, the wavelength of this photon stretches, and its energy decreases. This phenomenon, known as cosmological redshift, means that the energy of light emitted billions of years ago arrives at us with significantly less energy than when it began its journey. Dark energy exacerbates this effect, ensuring that even the most energetic photons eventually become incredibly dilute and low energy. This continuous stretching of space facilitated by dark energy provides an ever larger volume for the universe's total energy content to spread into, thereby driving its entropy higher and higher. It essentially ensures that the universe will never collapse back in on itself, a scenario that might have led to a big crunch and a potential rebirth, but rather guarantees an open, ever-expanding fate that ultimately leads to maximum disorder and thermal equilibrium. The relentless outward pressure of dark energy prevents any large-scale gravitational structures from forming or maintaining themselves indefinitely, thus ensuring that the universe cannot escape its entropic fate. It pushes the boundaries of the isolated system, offering more and more room for disorder to flourish. The universe is not just passively heading towards heat death. It is being actively propelled there by this pervasive, unseen force, stretching all potential and all differentiation into an infinite cold sameness. The universe, as we perceive it today, is a vibrant tapestry woven with the gravitational embrace of galaxies, the nuclear furnaces of stars, and the intricate dance of cosmic structures. Yet, this dynamic scene is but a fleeting moment in the grand cosmic narrative. As the accelerating expansion, driven by the mysterious dark energy, continues its relentless push, the influence of gravity, the architect of all cosmic organization, will begin to wane on ever larger scales. The stage is set for a profound transformation, a slow and quiet unraveling of the universe into an increasingly cold, dark, and desolate expanse. Imagine a vast, intricate web of cosmic filaments, where galaxies cluster together like beads on threads, separated by immense voids. This is the universe now. But as dark energy, a force that appears to have a constant energy density permeating all of space, asserts its dominance, it actively stretches the fabric of space itself. Gravitational attraction, which depends on the density of matter and radiation, becomes increasingly diluted as the volume of the universe expands. Dark energy, however, does not dilute. Its effect strengthens relative to gravity as space grows larger. This means that while gravity can still bind together stars into galaxies, and even galaxies into local groups, its power to hold together vast superclusters or to pull distant galaxies toward one another will be fundamentally overcome. The first casualties of this accelerating expansion will be the grandest structures in the cosmos, the superclusters of galaxies. These immense collections, spanning hundreds of millions of light years, are currently held together by a tenuous gravitational grip. Over the coming eons, perhaps tens to hundreds of billions of years, the expansion of space between these superclusters will accelerate to such a degree that their constituent galaxy clusters will be pulled apart. They will no longer interact gravitationally, effectively becoming isolated islands in an ever-growing sea of emptiness. Our own local group, a collection of over 50 galaxies, including the Milky Way and Andromeda, is gravitationally bound and is predicted to merge into a single larger galaxy in about 4.5 billion years. This cosmic island will remain intact, but all other galaxies beyond its immediate gravitational influence will recede from view, their light stretched by the expansion of space until it becomes effectively undetectable. What would this mean for the future night sky? For the inhabitants of our merged Milky galaxy billions of years from now, the distant universe would simply disappear. No other galaxies would be visible, even with the most powerful telescopes. The faint glow of the cosmic microwave background radiation, the echo of the Big Bang, would also be stretched to such extreme wavelengths that it would become imperceptible. The night sky would be a canvas almost entirely black, punctuated only by the stars within our own colossal galaxy, a solitary beacon in an otherwise featureless void. This increasing isolation signifies a profound shift. The universe, once a bustling metropolis of interacting galaxies, becomes a collection of increasingly lonely outposts. Within these isolated galactic islands, the stars themselves will undergo their inevitable life cycles, Stars are cosmic alchemists, fusing lighter elements into heavier ones in their cores, releasing enormous amounts of energy in the process. Our Sun, a yellow dwarf star, has enough hydrogen fuel to shine steadily for about 10 billion years. It is currently about halfway through its main sequence lifespan. More massive stars burn through their fuel much faster, living perhaps only a few million years before exploding as supernovae or collapsing directly into black holes. Smaller stars, however, are far more frugal with their fuel. The longest-lived stars in the universe are the red dwarfs. These stars are less than half the mass of our Sun and are incredibly efficient at burning their hydrogen fuel. Unlike larger stars, red dwarfs are fully convective, meaning their entire interior constantly churns, mixing helium produced in the core back into the outer layers. This prevents a buildup of helium ash in the core that would eventually choke off fusion. As a result, red dwarfs can slowly, steadily fuse their entire hydrogen supply over truly immense timescales, far longer than the current age of the universe. The most long-lived red dwarfs are predicted to shine for trillions of years, perhaps even up to 10 trillion or 100 trillion years. Consider the timescale. The universe is currently about 13.8 billion years old. Even the longest-lived red dwarfs will continue to burn for an era hundreds to thousands of times longer than the universe has existed so far. But even these enduring embers must eventually fade. After trillions of years, their nuclear fuel will finally be exhausted. They will not explode dramatically like supernova, nor will they swell into red giants. Instead, they will simply dim, shrink, and slowly cool, becoming what scientists hypothesize as black dwarfs, dense, inert spheres of helium, carbon, and oxygen, radiating away their last vestiges of heat into the cold vacuum of space. These black dwarfs are purely theoretical at this point, as the universe is not yet old enough for even the first red dwarf to have completed its lifespan. They represent the ultimate fate of the most common type of star, a slow, quiet expiration. As these colossal timescales unfold, the universe will progressively grow colder, darker, and emptier. The light from the last red dwarfs will eventually cease, plunging the cosmos into an epoch of profound darkness. Any remaining photons will be stretched to such long wavelengths by the accelerating expansion that they will carry almost no energy, rendering them effectively invisible. The average temperature of the universe, currently a frigid 2.7 Kelvin, will continue to drop, asymptotically approaching absolute zero, or 0 Kelvin. This means that the residual warmth from the Big Bang and from the activity of stars will be so diluted and spread out that the entire cosmos will become an unimaginably cold environment, devoid of any significant thermal energy. The emptiness will be equally extreme. Matter, already diluted by expansion, will be further scattered as any remaining unbound objects drift away from one another. The space between the isolated galactic remnants will become an almost perfect vacuum, far more pristine than any vacuum achievable in a laboratory. Any stray particles, such as electrons or positrons, will be so sparsely distributed that encounters between them will become exceedingly rare, if not impossible. The once vibrant and structured universe will become a vast, featureless expanse, a testament to the relentless march of entropy, which dictates the dispersal of energy and matter. What will remain in this desolate future? The universe will not be entirely empty, but its contents will be drastically simplified. The primary inhabitants of this future epoch will be the stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs are the dense, Earth-sized cores left behind by stars like our Sun. After they have exhausted their nuclear fuel and shed their outer layers, they are incredibly compact, packing about the mass of the Sun into a volume roughly the size of Earth, making them millions of times denser than water. They shine initially from residual heat, but without any internal energy generation. They slowly cool over immense spans of time. A typical white dwarf might take hundreds of billions to trillions of years to cool down to the ambient temperature of space, eventually becoming those hypothetical black dwarfs. Imagine a dying ember glowing faintly for an eternity before finally turning cold and dark. Neutron stars are even more exotic and compact. These are the collapsed cores of massive stars, roughly 8 to 30 times the mass of the Sun, that have undergone supernova explosions. They are incredibly dense, packing about 1.4 to 3 times the mass of the Sun into a sphere only about 20 kilometers, 12 miles, in diameter, the size of a city. A sugar cube-sized piece of neutron star material would weigh billions of tons. Neutron stars are supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect. Many neutron stars are born spinning rapidly and possess powerful magnetic fields, radiating beams of radio waves as pulsars. However, over countless eons, these pulsars will slow their rotation. Their magnetic fields will decay, and they too will cool down, becoming cold, silent, and incredibly dense balls of neutrons drifting through the cosmic void. Finally, the most enduring of all stellar remnants are black holes. These are the ultimate endpoints for the most massive stars, those exceeding about 30 solar masses, whose cores collapse completely under their own gravity, creating a region of space-time from which nothing, not even light, can escape. Stellar mass black holes, typically 3 to 100 times the mass of the Sun, will be scattered throughout the remnants of galaxies. Supermassive black holes, millions to billions of solar masses, reside at the centers of nearly all large galaxies. Unlike stars, black holes do not burn fuel or radiate light. They are characterized only by their mass, spin, and electric charge. For immense periods, they will simply exist, silently accumulating any stray matter that happens to fall into their gravitational wells. They represent the densest and longest-lived structures remaining in this incredibly distant future. Beyond these stellar remnants, there will be a sparse scattering of other objects. Planets that were once gravitationally bound to stars might be ejected into interstellar space as their parent stars evolve or as galactic interactions stir up their orbits. These rogue planets would drift in perpetual darkness and cold, their surfaces potentially frozen solid. There might also be a dilute background of fundamental particles that have not yet decayed, such as neutrinos and photons, carrying almost no energy, along with the elusive dark matter particles, whose interactions with ordinary matter are extremely weak. This epoch, often called the degenerate era, is the long, quiet unraveling of all cosmic organization built up over billions of years. The grand structures of galaxies, the luminous powerhouses of stars, the delicate balance of planetary systems, all will have succumbed to the relentless forces of expansion and entropy. There will be no more stellar births, no more vibrant nebulae, no more galactic collisions igniting new waves of star formation. The universe will be dominated by inertia and decay, a landscape of cooling embers and silent gravitational prisons, slowly but surely drifting toward an even more profound emptiness. This is not a sudden, cataclysmic end, but rather an infinitely slow fade, a gradual descent into a state of ultimate stillness and profound cosmic isolation. As the eons stretched into unimaginably vast timescales, The last glimmer of starlight had long since faded from the cosmic canvas. The universe, once a vibrant tapestry of galaxies, stars, and nebulae, had transformed into a frigid, silent expanse. The red dwarfs, those long-lived stellar embers, had finally exhausted their nuclear fuel, cooling down over trillions of years into dense, hypothetical black dwarfs. Objects that radiate almost no energy, essentially dark, inert balls of matter. White dwarfs, the remnants of sun-like stars, and neutron stars, born from more massive stellar deaths, had likewise cooled to near absolute zero, becoming mere gravitational ghosts drifting through the immense void. The era of active star formation and stellar illumination was a memory so ancient it predated the very concept of remembrance. In this profoundly dark and cold universe, where the accelerating expansion had long since torn apart galaxy clusters and even isolated entire galaxies from each other, only one class of colossal object persisted with any significant gravitational presence: black holes. These enigmatic entities, born from the most violent collapses of massive stars or grown to titanic proportions in galactic centers, were now the ultimate repositories of mass and the longest-lived structures imaginable. They were the last beacons, not of light, but of concentrated gravity, silent sentinels in a universe otherwise approaching the ultimate state of dilution. Let's take a moment to recall how these cosmic behemoths come into being. The most common type, stellar mass black holes, are the spectacular aftermath of stars far more massive than our Sun. When a star with an initial mass of at least 8 to 10 solar masses reaches the end of its life, it can no longer sustain itself against its own immense gravity. Its nuclear fuel depleted, the core collapses inwards at incredible speeds, often triggering a supernova explosion that blasts away the outer layers. What remains is a core so dense that its gravity overwhelms all other forces, compressing matter into an infinitely small point called a singularity, a case. Surrounding this singularity is the event horizon, a boundary from which nothing, not even light, can escape. These stellar black holes typically range from a few to a few tens of solar masses. Then, there are the supermassive black holes, which dwarf their stellar cousins. These giants, millions to billions of times the mass of our Sun, reside at the heart of almost every large galaxy, including our own Milky Way, where Sagittarius A holds sway. Their formation is a more complex and still debated process, likely involving the collapse of primordial gas clouds, the merger of smaller black holes, and the slow, steady accretion of vast quantities of gas and stars over billions of years. In the current epoch of the universe, these supermassive black holes still hold considerable gravitational influence over their now isolated host galaxies, even as the stars within those galaxies slowly dwindle and fade. In the far future we are considering, the universe has long passed its vibrant youth and middle age. No new stars are forming, meaning no new stellar mass black holes are being born. The existing population, however, remains. These black holes, whether stellar or supermassive, are no longer actively feeding on gas, dust, or unlucky stars. The vast reservoirs of interstellar matter that once fueled their growth have been either consumed, dispersed by stellar winds and supernovae, or stretched thin by the relentless cosmic expansion. They are isolated islands of extreme gravity in an ocean of ever-increasing emptiness and cold, silently drifting with the residual motion of their long, dead galaxies. Imagine standing on a hypothetical platform in this future universe, billions of trillions of years from now. The night sky would be utterly black, devoid of the familiar glow of galaxies or the twinkle of distant stars. The only light would be the faint, diffuse background radiation, stretched to extreme wavelengths by cosmic expansion, making it practically undetectable. Yet, scattered across this unimaginable vastness are these black holes. They are invisible, of course, their presence marked only by the absence of light and the subtle, almost imperceptible distortions they exert on the fabric of space-time. Their event horizons, once busy thresholds for infalling matter, are now quiet, reflecting nothing, revealing nothing. For an incredibly long time, black holes were considered the ultimate end state of matter, stable and eternal. Once formed, it was believed nothing could ever escape them, implying they would exist forever. This understanding changed dramatically in the 1970s with the groundbreaking work of physicist Stephen Hawking. He proposed a revolutionary concept, now known as Hawking radiation, which suggests that black holes are not perfectly black after all, but slowly evaporate over time. This seemingly counterintuitive idea arises from the strange and fascinating rules of quantum mechanics, particularly the concept of quantum fluctuations in the vacuum of space. Even in what we perceive as empty space, particle physics tells us that pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other almost instantaneously. These pairs, like an electron and a positron, are fleeting manifestations of energy borrowing from the vacuum, existing for such brief moments that they are usually undetectable. However, a peculiar situation arises precisely at the event horizon of a black hole. When a virtual particle-antiparticle pair materializes right at this boundary, it's possible for one particle to fall into the black hole while its partner escapes into space. When the particle falls in, it effectively carries away negative energy relative to the escaping particle. From an outside observer's perspective, it appears as though the black hole has emitted a particle, and in doing so, has lost a tiny amount of mass. This process, where a black hole slowly sheds its mass in the form of particles, is what we call Hawking radiation. Think of it like this: the black hole is slowly leaking its mass energy back into the universe, particle by particle. This means that black holes are not truly cold. They possess a temperature, albeit an incredibly low one, which is inversely proportional to their mass. Smaller black holes are hotter and radiate more intensely, evaporating faster. Larger, more massive black holes are much colder and evaporate at an excruciatingly slow pace. It's a subtle, almost imperceptible whisper in the cosmic silence, but it is inexorable. The timescales involved in Hawking radiation are truly mind-boggling, stretching human comprehension to its absolute limits. To grasp the enormity of these durations, consider that the current age of the universe is approximately 13.8 billion years, or 1.38 x 10 per 10 years. Now, let's look at black hole evaporation times. A stellar mass black hole, roughly the mass of our Sun, would take an estimated 10^67 years to completely evaporate. To put that into perspective, this number is a 1, followed by 67 zeros. This is longer than the current age of the universe by a factor of over 10 quintillion quintillion quintillion. It's a duration so vast that if you were to write out the number of years in seconds, you would fill entire books with zeros. Supermassive black holes, being far more massive, take even longer. A black hole with a mass of 10^8 solar masses, a common size for a supermassive black hole at the center of a galaxy, would require approximately 10^84 years to evaporate. And the truly colossal ones, those exceeding 10^11 solar masses, might persist for an astonishing 10^100 years. This number, a googol of years, represents a 1 followed by 100 zeros. It is a duration so immense, it makes the age of the universe seem like an instantaneous flicker. There are approximately 80 atoms in the observable universe. The evaporation time for the largest black holes is a number with more zeros than there are atoms in the cosmos. For the vast majority of their existence, black holes are effectively stable. Their evaporation rate is so infinitesimally slow that they lose mass at a rate far less than what they might gain from even the rare absorption of a stray photon or neutrino in the incredibly sparse future universe. The process only significantly accelerates towards the very end of their lives as their mass dwindles to a critical point. As a black hole shrinks, its temperature inversely increases, meaning it radiates more energetically. In its final moments, when its mass has become incredibly small, perhaps comparable to a mountain, the rate of evaporation would become catastrophic. The black hole would release its remaining mass energy in a powerful burst of gamma rays and other high-energy particles. This would be a final, brilliant, yet incredibly brief flash in the otherwise dark and cold universe. A last gasp of concentrated energy before the black hole vanishes completely. What is left after these ultimate gravitational prisons have evaporated? The universe will contain only a dilute soup of fundamental particles. Photons, the ubiquitous particles of light, now stretched to extreme wavelengths by cosmic expansion, making them almost impossible to detect. Neutrinos, those elusive, nearly massless particles. Electrons and positrons, the stable constituents of atomic matter, now unbound and incredibly far apart. And perhaps gravitons, the hypothetical particles of gravity, if they exist as discrete entities. There will be no complex structures, no atoms, no molecules, no stars, no galaxies, and no black holes. Just individual fundamental particles drifting ever further apart in an expanding, unimaginably vast and cold void. It is a profound realization that even the most extreme and seemingly immutable objects in the cosmos, black holes, the ultimate gravitational traps, are not eternal. They too are subject to the fundamental laws of physics, specifically the quantum mechanics that govern their evaporation. This means that the universe is not just losing its stars and galaxies, it is, in the incredibly long run, losing its very gravitational wells, the last remnants of complexity and structure. The triumph of entropy is absolute. Even these concentrated packets of order will eventually dissipate their energy into the void. One might wonder about misconceptions surrounding black holes in this context. It's often thought that black holes are like cosmic vacuum cleaners, indiscriminately sucking up everything around them. In reality, their gravitational pull is determined by their mass, just like any other object. If our sun were suddenly replaced by a black hole of the same mass, Earth's orbit would remain unchanged. We simply wouldn't have a star for light and heat. In this far future, with no matter left to feed on, black holes simply sit in their desolate space, slowly fading away. And the Hawking radiation itself isn't a bright light in the conventional sense, but a spectrum of emitted particles, a faint, almost theoretical glow from the quantum realm. The journey of the universe, from its hot, dense beginning to this unimaginably distant future, is one of continuous change and increasing entropy. The age of black holes, though lasting for durations that beg a belief, is merely another phase, a long, drawn-out twilight before the final absolute silence. These silent beacons, once the most fearsome and powerful objects in the cosmos, will ultimately succumb to the quantum whisper of their own demise, leaving behind a universe utterly devoid of structure or dynamism. The universe has spent unimaginable eons watching its last grand structures, the black holes, slowly dissipate. First, the stellar mass ones, then the supermassive behemoths at the hearts of galaxies, each one shrinking by emitting Hawking radiation, gradually fading from existence over timescales that dwarf the current age of the cosmos. A black hole with the mass of our Sun would take roughly 10^67 years to evaporate, while one as massive as a galaxy's central supermassive black hole, perhaps 10^11 solar masses, would persist for an astonishing 10^100 years. These numbers are so vast they defy human comprehension, representing a span of time far, far longer than the universe has existed so far. But even these ultimate cosmic prisons eventually reach their end, culminating in a final, barely perceptible burst of radiation as their last vestiges of mass energy convert into photons and elementary particles. With their departure, the universe loses its final significant gravitational wells, its last remaining centers of extreme density, and the last structures capable of holding any substantial amount of mass together. The stage is now set for the final act, an epoch of profound emptiness and stillness unlike anything that came before. This is the era often referred to as the eternal void, the ultimate state of heat death predicted by the laws of thermodynamics, relentlessly driven by the accelerating expansion of dark energy. Imagine a universe where the very concepts of here and there, bright and dark, hot and cold, have been stretched and diluted to their absolute limits. It is a universe that has reached maximum entropy, a state where all potential for change, for work, for structure, has been exhausted. There are no more stars, no more planets, no more atoms, and no more black holes. The grand cosmic tapestry, once rich with galaxies and nebula, has unraveled completely, leaving behind a fabric woven from threads so thin and so far apart as to be almost imperceptible. What remains is an almost absolute vacuum, a void so profound it makes the emptiness of intergalactic space today seem crowded by comparison. To put this into perspective, even the emptiest regions between galaxies in our present universe contain, on average, a few atoms per cubic meter. In the eternal void, the density of matter would be reduced to an infinitesimal fraction of that. Picture a cubic light year, a volume of space so immense it would comfortably contain our entire solar system many times over. In this future epoch, even such a colossal volume might contain nothing more than a handful of fundamental particles, perhaps a few photons or neutrinos, drifting in isolation, separated by truly astronomical distances. The universe becomes an expanse where the idea of collision between particles is an event so improbable it might never occur within any given localized region, even over aeons. Coupled with this extreme emptiness is an unimaginable cold. The temperature of the universe would approach absolute zero, 0 Kelvin, or approximately minus 273.15 degrees Celsius. This isn't just cold in the terrestrial sense. It is the theoretical limit of coldness, where particles possess the minimum possible kinetic energy. The residual cosmic microwave background radiation, which today permeates the universe at about 2.7 Kelvin, a faint echo of the Big Bang, would have been stretched and diluted by the accelerating expansion to energies so low they are practically non-existent. Its photons would be so redshifted, their wavelengths stretched to dimensions larger than the observable universe itself, rendering them effectively invisible, and undetectable. There are no pockets of warmth, no sources of heat, no energy gradients to drive any thermodynamic process. What then does exist in this ultimate void? The universe is not entirely empty, but rather filled with an incredibly dilute soup of the most fundamental particles. Predominantly, these are photons and neutrinos. The photons are the ghosts of all light that ever shone, from the Big Bang to the last gasp of the final evaporating black hole. However, these are not photons that carry information or illuminate anything. They are incredibly low energy, stretched out electromagnetic waves, so sparse and so redshifted that their individual existence is almost a statistical abstraction. Their wavelengths are so vast, their energy so minute, that they contribute virtually nothing to the overall energy density of the universe and interact with nothing. They simply are, drifting aimlessly through an eternally expanding space. Alongside these relic photons are neutrinos. These elusive subatomic particles were produced in vast numbers during the Big Bang and by nuclear reactions in stars. They interact so weakly with other matter that billions of them pass through our bodies every second, largely unnoticed. In the eternal void, these neutrinos too would be incredibly spread out and possess extremely low kinetic energies. They would represent a background sea of particles, but one so diffuse and inert that it could not possibly coalesce into anything or participate in any process. Their presence is a testament to the universe's past, but their current state is one of absolute cosmic irrelevance. What about matter particles? If the universe's expansion continues indefinitely and proton decay occurs, then even protons, the building blocks of atomic nuclei, will eventually decay into lighter particles like positrons and photons, albeit over timescales of 10 to 34 years or more. This is a theoretical prediction, yet to be observed, but it is a widely discussed possibility in the context of the universe's ultimate fate. If proton decay does happen, then the universe will eventually be devoid of all baryonic matter, all the matter that makes up stars, planets, and ourselves. What might remain are stray electrons and their antimatter counterparts, positrons, which did not manage to annihilate with each other during earlier epochs, or were products of proton decay. These would be incredibly rare, isolated particles, drifting alone, perhaps billions of light years from their nearest counterpart, never to interact again. If proton decay does not occur, then isolated protons would also persist, but still incredibly diluted and unable to form any structure. For the purpose of describing the most extreme end state of heat death, the scenario where even protons decay into lighter particles is often considered. And what of dark matter? This mysterious substance, which outweighs ordinary matter by about 5 to 1, interacts only gravitationally and perhaps weakly with itself, but not electromagnetically. If dark matter consists of stable, massive particles, they would also be diluted to an extreme degree by the accelerating expansion. They would drift through the void, completely isolated, unable to form halos or structures. Their gravitational influence spread so thinly across the vastness of space as to be utterly negligible on any local scale. They would be an invisible, inert component of the ultimate cosmic soup, contributing to its overall mass energy density, but playing no active role in its evolution or state. Crucially, in this state, there are no energy gradients whatsoever. An energy gradient is a difference in energy between 2 points, a fundamental requirement for anything interesting to happen. Imagine a hot object next to a cold object. Heat flows from hot to cold, performing work if harnessed, Imagine a high-pressure gas next to a low-pressure vacuum. The gas expands, doing work. In the eternal void, these differences have been entirely smoothed out. Every particle, every photon, every neutrino possesses roughly the same minimal energy, distributed uniformly throughout the immense volume of the universe. There is no hotter or colder, no denser or rarer. This uniformity is the defining characteristic of heat death. Without these gradients, there is no possibility for any process to occur, no way to extract energy, no capacity for change. The absence of energy gradients directly leads to the complete absence of structure. Structure, whether it's a star, a galaxy, a molecule, or a living organism, depends on localized differences in density, temperature, and energy. Gravity, which once sculpted galaxies and stars, has been utterly overcome by the accelerating expansion of space, which pulls everything apart on scales larger than the smallest quantum fluctuations. Electromagnetism, which binds atoms and molecules, finds nothing to bind. The strong and weak nuclear forces, which operate only over subatomic distances, have no meaningful structures left to govern. The universe becomes a featureless expanse, a smooth, undifferentiated medium where the very concept of object or form has ceased to be relevant. The universe is not merely dark, it is darkness beyond comprehension. There are no light sources, no reflections, no luminescence of any kind. The scattered, incredibly red-shifted photons are not light, in any sense we understand it. They carry no information, they do not illuminate, they are just a statistical presence. Similarly, while particles technically possess some minimal kinetic energy and are in motion, this motion is entirely random, isolated, and utterly incapable of leading to any interaction or the creation of anything new. Particles drift apart, their paths dictated by the expansion of space itself, never to meet, never to interact. There is no meaningful motion that could lead to aggregation, reaction, or evolution. The universe is frozen in a state of dynamic inertia, where individual particles move but the overall state remains unchanged. In such a universe, the very concept of time and change loses its conventional meaning. Time, as we experience it, is intrinsically linked to processes, to events, to the unfolding of cause and effect. A clock works because its gears move, its spring unwinds, its pendulum swings, all processes that rely on energy gradients and change. In the eternal void, where nothing happens, where no processes unfold, where there is no discernible change from one moment to the next, does time still flow? Philosophically, it becomes a mere mathematical parameter, a dimension along which nothing varies. From the perspective of any hypothetical observer, though none could exist, one moment would be indistinguishable from the next, stretching into an infinite, featureless expanse. The universe has reached its final equilibrium, a state where history has ended, and the future promises only more of the same, eternally. This is the ultimate end, a vast, featureless expanse, unimaginably cold and empty, where the fundamental laws of physics have played out to their final, inevitable conclusion. It is a universe in perfect thermal equilibrium, a state of maximum entropy, where the concept of energy itself has become so diffused and uniform that it can no longer power anything. It is a universe that has truly died, not with a bang, but with an infinite silent fade into absolute nothingness, save for the phantom whispers of elementary particles drifting forever apart. The grand cosmic story, which began with the incredible density and energy of the Big Bang, ends in this ultimate state of dilution and stillness. In essence, the universe becomes a perfectly flat, perfectly cold, and perfectly empty expanse, where the dance of creation and destruction has ceased, leaving behind only the most basic components, infinitely separated and inert. Our journey into the cosmic future has painted a stark picture, a universe slowly fading into an eternal cold and empty void, driven by the relentless march of entropy and the accelerating expansion powered by dark energy. This scenario, known as heat death, represents the most widely accepted scientific consensus, supported by current observations of the universe's expansion and its constituent components. Yet, the cosmos is a realm of profound mystery, and while heat death stands as the leading candidate for its ultimate fate, scientists have contemplated other, equally dramatic possibilities. These alternative scenarios offer glimpses into universes governed by slightly different fundamental parameters, reminding us that our current understanding, though robust, is still a work in progress. One such alternative is the Big Rip, a far more violent and sudden end than the gentle fade of heat death. This scenario postulates that dark energy is not merely a constant force, but one that strengthens over time, or more technically, its equation of state parameter, (2) falls below 1. If this were the case, the repulsive force of dark energy would grow so potent that it would eventually overcome every other force in the universe, including the strong nuclear force, the weak nuclear force, and electromagnetism, not just gravity. Imagine the current accelerated expansion of space becoming exponentially more aggressive, tearing apart structures not just on the scale of galaxy clusters, but progressively smaller and smaller scales. The Big Rip would unfold in a terrifying sequence. First, approximately 60 million years before the absolute end, the Milky Way and other gravitationally bound galaxy groups would be ripped apart, their constituent galaxies scattered into the accelerating void. Individual galaxies, no longer held together, would then begin to dissolve, their stars hurtling away from each other. Around 3 months before the final moment, our own solar system would feel the devastating effects, with planets being torn from their orbits around the Sun, their gravitational bonds overwhelmed by the rapidly expanding space between them. In the final minutes, the very atoms that compose stars, planets, and ourselves would be stretched and elongated, their electrons pulled away from their nuclei. Then, in the last fraction of a second, the nuclei themselves would disintegrate, followed by the fundamental particles, protons, neutrons, and electrons being torn apart. The universe would literally unravel into a superdiluted plasma of elementary particles, each isolated within its own rapidly expanding bubble of space, unable to interact, unable to form anything. There would be no light, no matter, no force capable of holding anything together. This is a universe that ends not with a whimper, but with an explosive, all-consuming shredding, leaving behind nothing but an infinitely expanding singularity of pure, empty space. While current observations strongly suggest that the dark energy equation of state is very close to 1, which points towards heat death, the Big Rip remains a fascinating, albeit less likely, theoretical contender, a stark contrast to the slow, cold demise. At the other end of the spectrum lies the Big Crunch, a scenario that was once considered a primary contender for the universe's ultimate fate before the discovery of accelerating expansion. The Big Crunch posits a universe where gravity eventually triumphs over expansion. If the total density of matter and energy in the universe were high enough, or if dark energy were to somehow dissipate or even become attractive, the expansion of space would eventually slow down, halt, and then reverse. Imagine the cosmic movie playing in reverse. Galaxies that once sped away from each other would begin to slow, then stop, and finally start rushing back together. The vast distances between galaxy clusters would shrink, and the universe would begin to contract. As the contraction progressed, the cosmic microwave background radiation, which we currently observe as a faint, cool glow at 2.7 Kelvin, would begin to blue shift, growing hotter and more energetic. The universe would steadily grow denser and hotter. Galaxies would collide with increasing frequency, their stars merging and disrupting. Eventually, all matter would be compressed into an unimaginably hot, dense state, collapsing back into a singularity, much like the conditions believed to have existed at the very beginning of the Big Bang. Some theoretical models even propose a big bounce, where this singularity isn't an absolute end, but a point of rebound, initiating a new Big Bang and a new cycle of cosmic expansion and contraction. However, current astronomical data, particularly the observations of distant type Ia supernovae that revealed the accelerating expansion, strongly argue against the Big Crunch. The universe is not slowing down. It is speeding up, pushing galaxies further apart rather than drawing them back together. The Big Crunch therefore remains a scientifically intriguing, but presently disfavored, alternative. Beyond these grand, universe-spanning scenarios, there's an even more exotic, highly speculative possibility known as vacuum decay. This concept arises from quantum field theory, which suggests that the vacuum of space, far from being truly empty, is actually a field of quantum fluctuations. Our current vacuum might not be the lowest possible energy state, but rather a false vacuum, like a ball resting in a dip on a hillside, not at the absolute bottom of the valley. If a true vacuum, a lower energy state, exists, a quantum tunneling event could spontaneously create a bubble of this true vacuum somewhere in the cosmos. Imagine a tiny, infinitesimal point in space suddenly transforming into a new, fundamentally different kind of vacuum. Once formed, this bubble of true vacuum would expand outwards in all directions at the speed of light, converting everything it encounters, matter, energy, and even the laws of physics themselves, into a new, unknown state. The fundamental constants of nature, the masses of particles, the strength of forces, all of it could change instantly and irrevocably within the bubble. From our perspective, such an event would be sudden, unpredictable, and absolute. There would be no warning, no escape. We would simply cease to exist in any recognizable form as the bubble washed over us. This scenario is profoundly unsettling because it doesn't just imply a cold, empty end or a violent tearing apart. It implies a complete rewriting of reality. Fortunately, there is no current observational evidence to suggest that we live in a false vacuum or that such an event is imminent. It remains a theoretical curiosity, a reminder of the profound depths of quantum physics and the potential for unexpected transformations within the fabric of existence. Regardless of which scenario ultimately describes the universe's far-flung future, whether it's the heat death, Big Rip, Big Crunch, or something even more exotic, contemplating these cosmic timescales places humanity's own existence into a profound perspective. The universe has been in existence for approximately 13.8 billion years, a span of time almost incomprehensible to the human mind. Yet, the timescales for the heat death of the universe extend for trillions of years, then quadrillions, then googles of years, a one followed by 100 zeros, before the last black holes evaporate. Our species, Homo sapiens, has existed for only a few 100,000 years, our recorded history spans mere millennia. Compared to the lifespan of a star like our Sun, which will burn for about 10 billion years, our entire civilization is but a fleeting flicker. When measured against the ultimate fate of the universe, our entire existence is less than a single breath in an unimaginably long cosmic lifetime. We live in a truly unique and precious epoch of cosmic history. This is a golden age for complexity, for structure, for life as we know it. Stars are actively forming in vibrant stellar nurseries, fueling galaxies with light and heavy elements. Planets are coalescing from the dust and gas around these stars. Complex chemistry is possible because the universe is still relatively young, still full of energy gradients, still far from thermal equilibrium. We can look up at a night sky filled with billions of stars in our own galaxy, and billions of other galaxies stretching across billions of light years. We can detect the faint afterglow of the Big Bang, the cosmic microwave background radiation, offering a direct window into the universe's infancy. This wealth of information, this abundance of light and matter, this very capacity for observation and understanding is a transient gift. In the far future, as galaxies recede beyond sight, as stars extinguish their fires, and as the last black holes evaporate, the universe will become utterly dark, cold, and empty. Future intelligences, if any, manage to survive through the vast intermediate epochs, would find a universe devoid of accessible information about its past. The cosmic microwave background would be stretched into oblivion, stars would be long gone, and the very concept of looking back would be meaningless. There would be no new stars, no new planets, no new opportunities for complex structures to form. Our current moment, with its vibrant galaxies and active star formation, with its capacity for life and consciousness, is a temporary phase, a brief window of opportunity for complexity and awareness to flourish. The scientific and philosophical implications of these cosmic destinies are immense. We study these far future scenarios not because we expect to personally witness them, nor because we can directly influence them, but because it is part of humanity's insatiable quest for understanding. It is the desire to map our cosmic destiny, to comprehend the grand narrative of existence from its fiery beginning to its ultimate conclusion. This pursuit of knowledge pushes the boundaries of physics, cosmology, and even philosophy. It forces us to confront our own transient nature, to grapple with the universe's indifference to our existence, and to appreciate the profound beauty and fragility of the present moment. It reminds us that even if our individual lives are short, and our species' existence a mere blink in cosmic time, the capacity to ask these questions, to seek these answers, and to marvel at the universe's grandeur is itself a testament to the unique complexity that has arisen in this particular vibrant epoch. So, as we conclude our exploration of the universe's ultimate fate, we return to the most likely scenario: heat death. The universe will continue its accelerating expansion, driven by dark energy. Over unimaginable spans of time, gravity will lose its cosmic tug-of-war, isolating galaxies and then dissolving them into their constituent stars. Stars will exhaust their nuclear fuel, fading into cold, inert remnants. White dwarfs, neutron stars, and the longest-lived black holes. These black holes, the ultimate gravitational prisons, will themselves slowly evaporate over trillions upon trillions of years through the subtle quantum process of Hawking radiation. Eventually, the last black hole will vanish in a final faint burst of energy. What will be left is an eternal void, an unimaginably cold, almost perfect vacuum. containing only a dilute soup of photons and neutrinos, perhaps some stray electrons and positrons, drifting infinitely apart. There will be no energy gradients, no structure, no light, no motion, a state of maximum entropy, where the very concept of time and change loses its meaning. This is the universe's long, slow journey towards an absolute cold, empty equilibrium. Yet, we must remember that this ultimate end is still unfathomably distant. The universe we inhabit today, the one we observe through our telescopes and study with our instruments, is teeming with life, light, and dynamic processes. It is a young universe, still in its vibrant infancy from a cosmic perspective, full of evolving galaxies, active star formation, and the potential for unimaginable futures. Our current understanding of dark energy and fundamental physics is still incomplete, and future observations from missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will continue to refine our models and potentially reveal new insights into the universe's ultimate destiny. The journey of scientific discovery is ongoing, and while the ultimate fate may seem bleak, the present moment, with all its wonder and complexity, is a precious, transient gift, a brief but brilliant flash of order and awareness in the grand, unfolding